So we will start by correcting the assignment together. In problem 1, using the false position method, find the root of the following equation, starting with a bracketing interval 0.1, 0.2, and a stopping criterion of 2% for the approximate relative error. So in this problem, we want to find the root with a 2% approximate relative error using the false position method. Okay, so the first step to do will be to replace CD by 0.1 to get f of 0.1, and replace CD by 0.2 to get f of 0.2. In this way, we can verify that they will have opposite signs. So the root, we will have a root in this interval, minimum a root, okay? But as I told you in this course, we will work on finding just one root, because if you have several roots, you can find them using this technique, okay? But then you will have to, even if you find one root, to continue. And if you know that there is several roots in your interval, you should continue to perform iterations to find other roots. But here we assume that we have just one root in a bracket, so we will just continue the operation until reaching this this value desired. Okay. Now, the first step will be to use the formula for the false position method. Since we are using the false position method, okay, the formula is XR is equal to X upper times minus F upper times X upper minus X lower over F upper minus F lower. Okay. Now here, for example, you can play with this formula. You can switch these two terms. So if you put X lower minus X upper, you should put here F lower minus F upper. And also, for example, another possibility, you can, instead of taking here X upper minus F upper times, you can apply X lower minus F lower times. Because at the end, when we derived this equation, we just replaced the coordinates of the upper point in the equation. So if you replace the coordinates of the lower point in the linear equation, you will still get a similar relation, but by switching upper and lower points. So it's equivalent. Okay. So here, starting from this formula, we just replace X upper here is 0.2. Here, for example, they considered X lower minus X upper. This is why here we should do F lower minus F upper, and this is F upper. Okay, so by just replacing F 0.1, F 0.2 by their values here in this equation, so this is F of 0.2, and this is F of 0.1. We can get the value of XR, the first estimate of the root in the first iteration. Okay. Now, what we will do, we should update the interval. We should check what is the new bracket we will take. To know, we will check for the sign of F 0.1 times F 0.1418. Another method, okay, some of you asked me in the other session, they asked me if we don't want to do the product, just we compare the sign. Also, it's feasible. You compare the signs. If for fx root you have the same sign of f 0.1, okay, this means that the root will be between xr and 0.2. While if 0.1, f of 0.1 and f of xr are opposite signs, then the solution will be in bracket 0,1 to xr. Okay, so here, to test if you have same sign or not, you do, here they did the product. Because the product is negative, this means that 0.1 and 0.141 have opposite f signs. So the solution, the root will be between 0.1 and 0.141809. So your new interval now, your updated interval will be 0.1. So the lower end will remain as it is. Okay, while you will update the upper end, which will become, instead of 0.2, 0.1418, because f of 0.141809 is of same sign of f as 0.2. Okay. Any question
Doctor?
until this
Yes.
stage? Yes.
دكتور بس سؤال لا بالنسبة للروot will you tell us in the exam to how many significant figures do you want it ولا نحن بننقي؟
Yeah, I will be, look, I can tell you, or I give you what is the criterion, or I will tell you the number of iteration to do.
لا دكتور I'm talking about the root مثلا هون the root is 0.14.
The number, you are talking about the number of digits
Yes.
after the comma here?
Yes.
Yes. In general, if I don't specify, take 4 to 5. Okay? So take
Okay.
4 digits after the dot. If you have the number, but also it depends on the number. يعني if you have a number 0.0000, إجباري يكون أكثر من 4 digits to be able to read it. Okay? But if you have a number like this, it's fine to stop here. يعني for significant. I'm talking about significant digits. Here, 4 significant digits are enough. Here, all these zeros, ما كأنهم موجودين. They will not do any contribution. So I should take, if I have, let's say, 1, 0, 2, 3, 4, 5, you can stop here. It's fine. Okay? So try to take 4 significant digits at least in the computation to not have a lot of round of errors.
Doctor, I have one more question on the exam.
Yeah.
Tomorrow. Regarding the carry on mistakes, and it's really easy مثلا إذا عندك a negative sign to carry on with the rest of the iterations مع هاي the negative sign which is wrong. So will you just keep on taking marks off ولا حيكون في carry on?
Can you just repeat? Can you raise your voice, please, if possible, because I'm not able to hear well.
Okay, just a second. Doctor, can you hear me better now?
Yes.
I was asking you إنه there's يعني في a high chance إنه نحط negative sign غلط or something because you know you're repeating iterations. So my question is that let's say I put -1 instead of 1 بوحدة من my calculations. رح ضلني عم بستعملها بعدين the next iteration واللي بعدها. So will you keep on removing marks ولا حيكون في carry on?
لا هلا أنا I will of course I will follow you. Okay. يعني I follow errors but please هلا أنا in general I don't care for calculation يعني أنا يعني other students who took with me other courses know that if the method is right I put the majority of the grade بس هيدا الكورس specifically كتير مهم I will follow you okay بس إنه إذا one error حتصير تجر لك كتير errors يعني أكيد I will put partial grade بس إنه okay you will lose يمكن you will lose maybe 30% of the grade لأنه ال calculation in this course is very important. Okay, بس إنه still I will put 70% in case the method is right. إذا just a small error of calculation أو شيء. Okay, مهم ما تكون ال method the way you are using the method is wrong. That's it.
Yes.
هلا try to do your calculate to be يعني try to be accurate and do and if possible يعني ما كتير تسرع على الكالكوليتر إنه do it in a fast way بس مش إنه بطريقة to do a lot of errors.
دكتور
Yes.
في مطارح مثلا اكيد بتعرف انه في مطارح فيني افوز انسر بدل ما ارجع اكتب مثلا انا بكتب لك على الورقه انه اخذت مثلا x1 هي 4 digits بس انا بدي ارجع استعمل هيدي الايكويشن احيانا احط انسر يعني
ما هي ما راح
كل
تفرق كثير يا كارين ما راح تفرق كثير اصلا اذا اوريدي حاطه 4 digits ما حتفرق الريزلت كثير اتس فاين.
اوكي
Okay, another question. Okay.
دكتور
Yes.
في اسال سؤال بالباور بالسلايدز تبع chapter 6.
Yes, tell me.
اوكي بسلايد
Do you want me to open it or you can just ask the question?
بليز اذا فيك تفتحيه من عندك.
Yes, which slide?
اوكي slide 17.
Yes.
اوكي دكتور، هون حطيت انه فينا نستعمل كذا ميثود وكل واحد الاريتيشن تبعها غير
Yes,
عن بعض، بس
exactly.
انه ليه مثلا نزلنا من 54 ل 17؟ انه شو السبب؟ هون ما عرفت كثير،
لأنه
كنت
أنت
عم
if you
بقرا.
draw this function, if you draw it between 0 and 1, هتشوف إنه هيدي الفانكشن is الbehavior تبعها in this interval is close to the linear profile. Because its behavior is not very far from the linear profile, the false position method will do a great work. It will be much faster than the bisection method. Okay? And for the open methods, اللي هن الsecant اللي هو Newton-Raphson, in general, when you have the behavior of the function not involving changes, slopes, inflection points, they will perform also much better than bracketing techniques, especially if you start with initial guess that is appropriate. يعني هون if you start by initial guess for secant, let's say if you consider x 0, x1, اللي هن 0, 1, if you start by these two guesses, you can have a very good result with the secant. نفس الشيء for Newton-Raphson. Newton-Raphson you expect also it behave better than secant لأنه it will give you the actual tangent line. الsecant بتقرب على Newton-Raphson لما تكون ال two initial guesses قراب على بعض. يعني in this way you will be closer to the tangent line when you do your iterations. Okay? So
اوكي
في
شيء
functions يلي ما عندهم functions مثل هيدي يلي ما عندهم high slope variation يلي behavior تبعهم is close to linear behavior بيكونوا in general الorder أحسن هيك. يعني بيكون البايسكشن بدها أكتر شيء يرجع على false position بيرجع على secant بيرجع على Newton-Raphson. Yes.
اوكي دكتور، ثانك يو.
Doctor?
Yes.
Sorry, I remember the question. بس بالexam to save up on time,
Yeah.
for example, إذا أنا قلت لك if we're taking the first iteration, the first step, we checked إنه f lower times f upper is less than 0, so I already calculated f lower. ففيني مثلا فيني بالفاينل ستيب لما بدي أعمل f lower times f root.
مش ضروري تعمل multiplication. فيك دغري تقول إنه هي same sign أو opposite sign, so I take this interval.
Oh, okay, great.
بس مهم تكون جبت ال f upper lower تقدر تعمل comparison.
Yes, of course. أنا my question إذا جبت مثلا let's say any value مثلا f upper إذا جبتها مرة وبدي أرجع أستعملها مرة تانية في ما أرجع أحط لك numbers وأحط f upper دغري الأنسر.
Yes, exactly. إذا حطيتها one time or
yes, حطيتها one time.
Yes,
but I don't have to show it twice. Okay, great. Thank you.
Yes, it's fine.
Doctor?
Yeah.
Can you just repeat شو قلتي عن table آخر شيء لأنه you lagged شوي ما قطشتي.
Okay,
إذا بس هي table
Yeah, I was saying هون, you mean this slide?
Yeah, the slide.
I was saying that if you have a function that is not including high change in slopes, it's not including maximums and minimums, it's not including inflection points, okay? And its behavior is close to the linear one. Expect then إنه Newton-Raphson will be the best option. بعدها بيجي السيكنت، بعدها الفولس بوزيشن، وبعدها البايسكشن ميثود.
Okay, thank you.
Okay.
Thank you.
Okay. هلا concerning yes.
الكوادراتيك convergence فيك بس بليز ايديا شوي. أنا بعرف الفورمولا.
Okay. هي شو فكرة الكوادراتيك convergence؟ إنه mathematically they proved إنه we can for the Newton-Raphson method if we do mathematical analysis we can prove إنه الerror تقريباً okay is of order الerror at I plus 1 is of order f second over f prime على root times الerror at iteration I square. okay. فشو الفكرة هون؟ الفكرة إنه إذا أنت عملتي already calculation let's say طلعت أول error let's say 1 for example أو 1 point أو 0 point let's say 5 okay. عتاني stage طلعت الerror أصغر 0.25 مثلا. You expect very high convergence. Why؟ لأنه أنت هون كنت عم تحطي 0.5 square. مرة الجاي حتحطي number أصغر منه عم تعمليه square. يعني already كارين أنت عندك الerror صغرت لأنه صارت over 2 وزيادة عم بتحطي square. يعني بدل ما تكون بس الايرور عم تصغر by 2 عم تصغر by order 4. يعني صرنا عم نعمل هلا 0.25 square. This is why هيدي الريليشن اللي you can mathematically prove it. هلا انتو you are not responsible of the proof, but just you should know انه we can prove انه بالنيوتن-رافسون method we have this correlation بين error at iteration I و at iteration I plus 1. So in this case لما تكون على I plus 1 الerror عم تصغر فبتصير convergence very fast. لأنه لاحظي coefficient هون. إذا عندي error at a certain iteration 1 10 minus 2 ثاني مرة بتكون of the order 10 minus 4 لأنه you are doing now you are putting it and doing it square. بترجع بتصير 10 minus 8 بترجع بتصير 10 minus 16. So once it start to decrease, it will continue to decrease in a very fast way. Okay, this is why we say in Newton-Raphson method the convergence behavior is quadratic. بينما لو كانت الريليشن مثلا لو انت ثبتتي انه الريليشن another example another method let's say نحن شفنا قبل الميثودز تبع البايسكشن وهيك رسمنا الايرور فاريشن طلع تقريبا linear. يعني in this case إذا طلع لك relation إنه error at I plus 1 is a certain factor coefficient A times error at iteration I يعني في مثل بيصير behavior linear يعني linear decrease of the error. بينما هون إذا في decrease حيكون quadratic يعني حتكون أسرع بكتير it's much faster decrease. اوكي
اوكي دكتور مثل ما لقينا الريليشن شيب بين الايرورز بالبايسكشن هون نفس الشيء.
هي نفس الشيء. هلا انت تتوصلي لهيدي بدك ماثيماتيكال تولز. انتم مش مسؤولين عن الماثيماتيكال ديريفيشن بس هي نفس الكونسبت. يعني هن من وين بيجيبوهم؟ بيجيبوا اصلا الايرور من شو اجت بيعملوا لها ديريفيشن للايكويشن تبعها وبيشوفوا and they relate الايرور على الاي وعلى الاي بلس 1. نحن قبل بالبايسكشن عملنا numerical calculation and we did the graph of error بين معنا انه هالincrease is nearly linear. اوكي وحتى قدرنا فينا نجيب relation بما انه نحن بنعرف انه بالبايسكشن for example at each step we divide the interval by 2 يعني we can assess how it's reduced. اوكي هون عملوا mathematical formulation to find لقوا انه relation quadratic فاذا it's much when we have convergence it's much faster. بس هون المشكله انه we might have divergence لانه هيدا relation اذا بالعكس اذا شي مره عم تعملي iterations وعم يطلع لك اي تي اي بلس على الاي بلس 1 اذا على الاي بلس 1 عم تطلع الايرور اكبر من على الاي اتس بروبلم لانه شو رح يصير؟ حيصير بعدين هيدا الديفرنس حتكبر مع الوقت لانه اتس سكوير. سو الحلو بالبراكتنج ميثود انه convergence is guaranteed لو كانت linear يعني هي ابطا بس guaranteed. بينما بالاوبن methods you have this relation بس هيدا عندها positive effect in case I have a convergence trend حيكون very fast بس كمان إذا عندي divergence حتكون كمان divergence can be very fast. يعني هون I can have divergence في نيوتن-رافسون بينما بالbracketing method I cannot have divergence.
اوكي دكتور يعني مشان هيك بنقلها when it converge fast لأنه الconvergence تبعها هي quadratic.
صح yes exactly. يعني ال behavior is faster من ال linear behavior because it's square. Okay. Any other question on a slide in chapter 6?
دكتور
Yes.
بس لا تعطينا جراف وتقولي لنا انه which method is suitable for this رح تحددي لنا الانترفال.
Yes of course.
Okay.
So going back to the assignment, okay? So we were talking about how to find the root in a first iteration using the false position method. So now already from the first iteration we got an updated value. Here 0 point la root. This is the first estimate of the root, okay? In order to calculate an approximate error, we should have another estimate. Yani we should perform another iteration to compare with. So now the next step, we said that the new interval will be 0, 1, 0.14, etc. 1809. So now we will apply again the same relation, but now we updated x upper و x lower. يعني بقت ال x lower نفس الشيء بس x upper was updated. So here then in your equation x upper becomes, instead of 0.2 you have 0.141809, and instead of f upper you will replace f at 0.141809 اللي هي when we computed here, it's minus 0.03521. So we replace it here. This is f at x upper, which is here 0.141, etc. Okay, and times x lower minus x upper over f lower minus f upper. So we just replace the expression of f at 0.1 and f at 0.141, and then we get, this is the second estimate of the root. So now we have two estimates from two consecutive iterations. So to know what is the relative approximate error, we compute the absolute value of xr at state 2 minus xr at state 1 over xr at state 2. And what is nice here is that from the first two iterations, the approximate error resulting was already satisfying the stopping criterion. And the stopping criterion is 2%. So I can stop here. No need to do any other iteration. If the stopping criterion was less than 1.17, and 1%, for example, then I say, no, it's the approximate error is higher than 1. So I should continue. So I should perform a third iteration to see if I can stop at the third or not. Okay. Any question on this problem? Okay. Problem 2. We give the function f of x equals to minus 12 minus 21x plus 18x squared minus 2.75x cubed. Using the bisection method, find the root of the given equation, starting with a bracketing interval of minus 1, 0, and the stopping criterion of 1% for the approximate relative error. So here they gave us what method to use. We want to use bisection. We have the initial interval and we have the stopping criterion. We have everything we need. So all we have to do is to start for the bisection method. It's the easiest estimate of the root. You take just the middle of the interval. So xr1 is minus 1 plus 0 over 2 is minus 0.5. Now, the next step will be to check for f of minus 1 times f of minus 0.5. Or as your friend said, it's enough to get what is f minus 1. F minus 1 is positive, and f minus 0.5 is also positive. So since f minus 1 and f minus 0.5 have the same sign, okay, so the root will be in the other half. Yani it will be between minus 0.5 and 0. While if minus 1 and minus 0.5 have opposite f, then the root will be between minus 1 and minus 0.5. So here, since I have same sign, I can directly say minus 0.5 will replace minus 1, and the new interval is minus 0.50. And now I am ready to do a second estimate of my root by taking it as the middle of my interval. So xr2 is minus 0.5 plus 0 over 2 is minus 0.25. And now I can calculate the first approximate error between these two. So I get that already I have a very large error at the beginning. My error is 100%. So I can expect here, I should do several iterations if I want to reach 1%, because epsilon is very large from the beginning. Okay, so let us continue to perform. We can perform iterations using the same procedure. Okay, this is why, because it will take some time. We summarized the results in a table. So in each step, same approach. Okay, now I want to find what is the new interval. Okay, so I should compute f at minus 0.5, f at already calculated from the previous step. I should now compute f at minus 0.25. Since they have opposite signs, so I can say the the root is in between. Okay, so in the next step, I will take XR as minus 0.5 minus 0.25 over 2, and then I will repeat this procedure until reaching an absolute error smaller than 1%. And as I told you, since the initial error was high, I will expect that I need several iterations to be able to close to 1%. So here I need to perform 8 iterations, okay, to reach the value I need. If you want also here, we can consider that in the first step, okay, as a first step, I take the initial interval they gave me. This is my first estimate of the root, and I will continue to update my estimate until getting a relative error between the new value and just the value before it, which is called old value. The difference between them when I compute the relative approximate error would be smaller than 0.1%. Sorry, smaller than 1%.
دكتور
Yes.
هون أنا إنه بس شوف بايسكشن طبق الفورمولا طلع معي n equal ل 6.64 يعني أنا كتبت 7 iterations
لا كارين،
وبوصل ل R8.
انتبه على شغله، هيدي الفورمولا تبع الكور هيدي للابسوليوت ايرور مش للابروكسيمت ايرور. بليز انتبهوا كثير قروا منيح السؤال. اوكي، في عدة تايبس اوف ايرورز. في الابسوليوت ايرور اللي هي الماكسيمم possible error you can have اللي هي length of the interval. فاكيد يا كارين الماكسيمم ايرور absolute error فيك توصلي لها بإتريشن اقل، بينما اذا بدك الابروكسيمت ايرور اصغر من الابسوليوت ايرور. اوكي، سو بدك iteration اكثر فتقدري تو ريتش الكرايتيريا اللي انت بدك اياه. اوكي، يعني انت الايديا انه الريلاتيف ايرور هي just taking the difference in length. اوكي، اصلا الابسوليوت ايرور ما لنا a percentage. الابسوليوت ايرور كارن الابسوليوت ايرور هي difference in length. يعني انا اذا ببلش لك من interval 0 1 وبقول لك انه desired value هي let's say 0 point الدلتا، يعني الدلتا اي عند 0.01. هي منا percentage، هيدي الديفرنس. يعني انا بدي اوصل لانترفال يكون اللينث تبعه 0.001 ويكون في بقلبه الروت. اوكي، هلا اذا بدك فيك تقولي انه انا if I reach this value of the error، يعني انت هون هيدي ال 1% منا هالفاليو، هي percentage. فانت اذا بدك تحكي ب absolute error بدي اعطيك الفاليو تبعها. let's say for example انت اخذتيها 0.01 يمكن، صح؟ لانه اعتبرت انه ال 1% هي الابسوليوت ايرور. this is what you did.
أنا فكرت بالبايسكشن فينا كل مرة قبل ما نطبق الميثود طبق هالفورمولا تشوف أنا how much do I expect iteration. فكرت
how much you expect iterations للapproximate او لانه هي غير فورمولا للapproximate. انتبهوا هن في فورمولا للapproximate error بس نحن ما
تبع
اخذنا.
اوكي لكن اللين منا يعني هاللوج ما فيني استعملها.
منا للapproximate هي للabsolute. you can derive a relation للapproximate. you can do it. هي same concept يعني بس تفرق شوي. يعني you can try to derive it, you can do. اوكي، وحتى في عده فورمولاز. في وحده اذا بدك تاخذي البرسنتج اناليسيس غير ما يكون بس بدك الايرور، لانه في كرايتيريان للبرسنتج، في كرايتيريان للجاست الفاليو اوف ذا ايرور. اوكي، يعني هون مثلا الابسوليوت ايرور ما بيسالوها كبرسنتج، بيسالوها كفاليو، يعني دلتا اللي هي اللينث اوف ذا انترفال. اوكي.
Yes, doctor.
So here you can find how many iterations are needed by doing the procedure. And I will continue to iterate until reaching the desired point. Okay. Now, another problem. Using the false position method, find the root of the given equation, starting with a bracketing interval -1, 0, and the stopping criterion of 1% for the approximate relative error. هلا هون مثلا okay they are asking for the same problem to use the false position method instead of the bisection method. Okay, so here in such problem you can compare the behavior of the two techniques, and you can expect the result if you if you draw a function. And if you draw it, you can see if the behavior of the function is close to linear or not. If it's not highly nonlinear, you expect a false position method will do a better job. Okay, and this what will happen here, because here instead of 8 iterations, you will just need to do 5 iterations. Okay, so you can start with the initial estimate, since you know that your initial interval is -1, 0. So now here, just instead of taking just the middle, you should apply the formula for false position. For false position method, the formula is XR equal to X upper, اللي هي هون 0. So this is X upper minus F upper. So you compute F at 0 and you replace it here. So F upper times X lower minus X upper over F lower minus F upper. So you can get the corresponding value of your first estimate, XR at estimate at stage 1. And now to update, يعني بس the only difference with the bisection method here, the way we do the estimation of the root. Once you do the estimate of the root, then the procedure will be the same. I will compute F at XR to see if it has the same sign of -1 or not. So here they have opposite sign, so you can be sure that your root is between -1 and -0.287425. So you update your interval and you say now my root is between -1 and -0.287425. Okay, so now you will apply the same formula, but now you will replace X upper by, instead of 0, by -0.287425. And of course, F upper you updated, X upper you updated. Then you get the new estimate of the root. This is estimate 2. So now you will be able to calculate the first approximate error due from the first 2 consecutive iterations. Already, it is much better than bisection, because if you remember the bisection method, we started by 100%. Here we started by 24.25%. So we can already expect that the false position method, I will need a lower number of iterations to reach my solution. So now I will repeat the same procedure several times until reaching an approximate relative error lower than 1%. So this is what we performed here. We did it. So we did the 1, 2, 3, 4, 5. Okay. So here we were able to reach the desired criterion after 5 iterations. Okay. So the false position method was faster in convergence than the bisection method. You can justify this by the behavior of your function. The behavior of your function is close to linear behavior.
دكتور
Yes.
بس بهيدا الكويشن الفانكشن كانت of degree 3 بس يعني بهالانترفال -1 و 0 بتكون هي approximately يعني بتكون straight line عشان هيك
مظبوط صح exactly.
بس إذا أخذنا another interval بتكون
مظبوط.
يمكن
It depends a lot
أحسن.
on the interval. Exactly. It depends on the interval you take. Okay. Of course.
Yes.
Yes.
Thank you, doctor.
Yeah. Now, in problem 3, using the bisection method, starting with a bracketing interval from 10 to 45, find the number of iterations needed to achieve an absolute error below 0.05. Again, read well the given. Okay, read well the given to know what you should apply. Here, a lot of you asked me, you didn't give us the function because you don't need it. Okay, so read well the given to know what you should use. So here you just need the interval, the initial interval, and you need the absolute error you achieve. So as I told you, Karen, هيدي الفورمولا هي مش للpercentage. Okay, هي الفورمولا to get just absolute error equal to below 0.05. Okay. So now this formula you can apply it. هلا بالcourse انتم متعودين على ln, you can use ln. Okay, no need to use الفورمولا تبعهم. فينا نستعمل log base 10, فينا نستعمل log base 2, بس كلهم بيعطونا نفس الريزلت as I told you. If you are familiar with ln method, use ln بالcalculator. Okay, so using the formula developed in the course material, we have delta x, which is the initial length of the interval is 35. We have that the error is 0.05. Okay, so now all you have to do is to replace and get n, and of course you should round up to the closest integer. So here you have 9.45, so I need to perform